么上个礼拜我们著作已经有稍微介绍一下我们这个 System ID 的这个大纲了啊。那我们大概要教什么？那今天我先把什么叫 Apply System ID 稍微介绍一下。那你们为什么要学？这边电机系的举手，有没有？工科系的。还有其他系的是土木的，这不是水工学，对吧？也是不错的 ，OK。那你可以想象得到，那么现在System ID 在各个领域上都有用到了，应该是这样讲。那么我今天是介绍大概1970年到80年代为什么那么当初 NASA 因为我在 NASA 工作当初 NASA 为什么对这个题目特别有兴趣从那时候开始。虽然 System ID 本身的方法真正的方法论真正方法1960几年代就开始有了，但是那时代因为 computer 还不是很快那时候 computer 现在的像这样的一个 notebook 这样大小的一个 notebook，1960年代的 computer 是一个大的空间，像一个大的教室一样。我在念书的时候，成大有一个叫做130 IBM 130，那个占的空间是比这个教室还大。那它的速度还有它的储存量比我们现在的 notebook 还小，当初是这样子。所以很多的方法虽然已经有一些雏形，但是不能用，因为电脑没有那么快，也没办法处理那么多的 data。但是到大概80年代70到将近70年底的时候，80年代的时候 ，IBM 0360等等这些都出来了PC， 我们现在的 PC 我们那时候叫做 Macintosh， 就是真正在桌子上有桌上的电脑也是 Steve Jobs 刚刚开始。那我们当初也都是用 Steve Jobs 的 Macintosh， 老师家里还有一台 Macintosh， 跟现在比当然差很多了但是当初已经算是很不错了。所以在那个时代那么NASA 就开始发展很多深太空的探索。那60年代都是进太空的，像到月球，这个大部分都是进太空，就是说地球旁边的。那到1970年底开始，那美国 NASA 就开始往这个深太空，我们所谓深太空就是到什么火星木星等等，我们太阳还是太阳系里头的。那假如要到那种的，就是深太空的人造卫星，就不是像我们现在的，像1960年代只有一个送这个小小的3个太空人就挤在一个很小的空间里头了那人造卫星就越造越大。那越造越大有什么问题人造卫星像101跟我们工科系这一栋大楼，那么101跟这个大楼有什么不一样？你觉得有什么不一样？自由度变多。这个大楼理论上自由度也是很大。那101假如地震来的时候，谁比较危险？101比较危险所以我们这里比较危险。101比较危险，为什么？因为它是比较我们讲说比较 flexible， 所谓 flexible 就是它比较软的，好，叫 flexible。同样的，在人造卫星也一样，越造越大的话，它就会比较 flexible。那在1980年初的时候啊，那美国就在太空NASA 就是想说，我们要送一个这个 Galileo 的这种这个 spacecraft， 就是这个人造卫星啊，到 Jupiter。那为什么我们要到 Jupiter？ 你们晓不晓得为什么？那时候美国这个太空这个 NASA 想到 Jupiter， 都有原因的。美国NASA 每发展一套技术啊，都是跟它任务有关的。它不会凭空去想象说要来找一些什么技术，这个跟任务无关的，都这样想。那我们为什么美国为什么想到 Jupiter？ 你们晓不晓得什么原因？啊？你怎么说晓不晓得什么原因？哦，有个外籍生啊 ，OK， 好，不好意思啊。All right, now we start speaking English. The question is, why NASA is interested in building a large spacecraft going to the Jupiter? Why? You know why? You want to make a guess? Well, you can speak Chinese. That's fine to me. I can translate. Why? Because we are very interested in seeing any creature or any human being in our solar system. Right? Do we have any water in Moon? Is there any ice or any possible environment similar to our environment in Earth? Right? Okay. So somebody saying that any being, we say any maybe a small cell, why our Earth has human being or any other animals that other stars don't have. There's no reason. But if you want to find out whether there is any existence, any life in any other star or any other planet, the first job you have to do is there any water? Because if there's no water, there's no life. So if you look at this, Galileo, the mission of Galileo, if you look at the next one, the mission of Galileo is going to the Jupiter. It's not Jupiter itself. There are many moons orbiting the Jupiter, and there are 1 or 2 moons around the Jupiters. And the scientists find out that there are a strong possibility they have water in the moon. Okay, so this is the just the sketch of the Jupiters. This is Galileo mission's coloring book. So the coloring book means that they are milestone. So how they are going to fly, when they are going to fly the Jupiters, and how soon they will arrive the Jupiter. This is the we call the cookbook, like a cookbook. So you can see that 1989, October 18, that's the space shuttle launch. And the Jupiter is packed inside the space shuttle. And then from space shuttle, then we'll also eject from the space shuttle, and then they will fly to Jupiter. Okay. Now, our interest is the systematic, why we want to do systematic for the Jupiter structures. So, I think you can go to our NASA website. There are some many informations regarding the Jupiters and also the Galileo spacecraft. So I am not going to talk about that much, but there are certain moons like Io, we call hot Io. Now, Io has volcanic activities. So, if we have a volcanic activities like Earth, so we have a volcanic activity on Earth. If there are any volcanic activities, that means there's a possibility. There's an atmosphere. All right. If there's an atmosphere, means we have oxygen, or we might have if we have oxygen, that means we might have water. So that's one of the moon NASA is interested. And there's another moon called IC Europa. On the right hand side, you can see the IC Europa. The IC Europa, the Europa is covered by the liquid called liquid oceans. And that liquid ocean doesn't mean it's water, but as long as the liquid ocean means there is a possibility that there's some water inside. Okay. And this is the again what they think they're supposed to see. All right. And there's the called Galileo science images. This is all the pictures taken by Galileo spacecraft. And anyway, we are not talking about Galileo. We are not talking about science in these lectures. We are talking about the systematic. All right. Now I'm going to skip those. I'm going to look at this spacecraft. So this is called Galileo spacecraft in launch configurations. And what we mean in launch configurations means that they are certain, they are packed. All right. Now before we launch for any spacecraft, before we launch, what we have to do. Because if you launch by rocket, there's the gravity is about 10 times of the Earth gravity in terms of accelerations. So when you launch, that means this spacecraft will be 10 times heavier. 9 to 10 times heavier than on Earth, because there's accelerations. 有一个加速度. Right? Can this structure tolerate this 9 to 10 times gravity force? We have to test it. Okay? That's why we need to go to our laboratory to test, see if this structure will be able to suffer the gravity, the acceleration force because of launching. During the launch, there are also a lot of vibrations, right? Because a rocket going up, and there's a lot of vibrations. Now, the structure like this, if you don't tighten enough, or you don't have a good design, then what happens? Because the force is very strong. You are thinking about if you, on the earth, you are a person with 50 kilograms in a launching mode, means you are almost like 500 kilograms. It's very heavy, right? Of course, it depends on how fast you want to go to the space. That's one other questions. So at that moment, what we need to do for this spacecraft? Now, inside the laboratory, what kind of test you need to do? What kind of test you need to do? The first task we want to do is, can this structure tolerate the vibrational motions due to the launching force? Now, if you look at the structure, what kind of property on the structures we are looking for? What kind of the characteristics of the structures we need to be watching? All right, when you walk on a bridge, we know that if there's a team of 50 people walking on a bridge, what do you need to do? You don't want to match, right? Because of frequencies. If you happen to be matching your team of 50 people on the same frequencies as the bridge, then what happens? You will break the bridge, right? Because there are oscillations of the your matching frequencies, and the structural frequencies are oscillating. So, when we test these structures, we want to find out what kind of frequencies of these structures you have, like a Type A 101. The frequencies of Type A 101, if it happen to be the same frequencies as earthquake frequencies, then you better not be inside the 101. Because the 101 frequencies will oscillate with the earthquake frequencies. That's very dangerous. If your earthquake frequency is different from the 101 frequencies, then you are safe. That's the point. Now, how can we compute the structural frequencies of this configurations? How can we do it? They're done. Is it okay now? It's okay, okay, all right. I thought it's interrupt again. All right. Now, to understand also to compute the frequencies of the structures. Then what should you do? 你要怎么做？
那个结构的
举例。
给它一个简洁外力，测它的反应。
Okay. So the students say, I'm asking a question, how can you compute or how can you determine the frequencies of the structures? There are two ways to do it. One way is go to do the, we call finite element analysis by giving the structures rigidity, right, the Young's modulus and rigidity, and you might be able to compute from that Young's modulus, and then we will be able to compute the frequencies of the structures. That's by analysis. Just another way is by going to the laboratory, giving external forces to the structures and look at their behavior. Right? Look at their behavior. So if I have if I have a structures, say assume I have a structures, this is my structures. Alright, that's my structures. Alright. There's a very simple structures like that. Alright, and this is my ground here. If I give a force here, like here, force here, and I measure my output, this is my output, this is my, this is my displacement. So I measured my displacement. This is the force. This is the force. Give the force. Normally we give them random force, or what we call random force. Alright, so we give a random force, then we measure their displacement. For example, if we can measure their displacement at this the end of the structures, then we call this we call the input data. This we call the output data. Right? So if we give the input data to excite the structures, this is the structures, then we have an output data. The output data can be displacement, can be velocities, can be accelerations. And I just write down here displacement, but can be any other quantities. So given the input data and we saw output data, this is what we are giving, this is what we have measured. So this is the giving. This is what we measured. Alright? Given the input data and also the we have the measure data, based on these two data,